We have already studied about electric field. What is electric field? Electric field is a region around electric charge in which another charge experiences force. Can we see electric field? No, electric field is invisible. Then how to represent it? For representing electric field, Michael Faraday introduced a way called electric field lines, also called as lines of force. Electric field lines are a way of pictorially mapping the electric field around electric charge. That means electric field lines are imaginary lines drawn to represent electric field. Using field lines, we can visualize direction of electric field and also strength of electric field. Then how to draw electric field line? We will see the properties of field lines. We know electric field is a vector quantity which has both magnitude and direction. Usually, how do we represent vectors? Using arrows. If we consider point charge, positive point charge, the direction of electric field due to positive point charge is radially outward. It is outward in all the direction. We can represent electric field due to point charge using arrows like this. Here arrowhead represents direction of electric field and arrow length represents strength of electric field. But it is difficult to draw arrows at every point all the time. So instead of drawing countless arrows, we draw smooth line called electric field line. If we draw smooth line, how it represents direction of electric field? The tangent drawn at any point will represent direction of electric field at that point. For positive point charge, the direction is outward. For negative point charge, direction is inward. How it represents strength of electric field? Closeness of lines or density of field lines will represent strength of electric field. While drawing field lines, I may draw some lines. You may draw more number of lines. Then what happens to closeness of lines? Here it is relative density or relative closeness of field lines. That means closeness of field lines compared from one point to another point. For example, near the charge lines are close together. This shows electric field is strong. At larger distance, lines are far apart. This shows electric field is weak. Hence, if lines are close together, it shows electric field is strong. If lines are far apart, it shows electric field is weak. The tangent drawn at any point will represent direction of electric field at that point, and relative closeness of field lines will represent strength of electric field. When we draw field lines on board or paper, it seems two-dimensional, but electric field is three-dimensional. In 3 dimensions, how to represent strength of electric field? Imagine a point charge, positive point charge. These are the field lines due to point charge Q. In 3 dimensions, consider small area element perpendicular to electric field. Now, number of field lines crossing this area will represent strength of electric field. So, strength of electric field is directly proportional to number of field lines crossing unit area. And next important point is, for a point charge, electric field varies inversely as square of the distance. That is, E is inversely proportional to R square. How field lines represent this relation? This is the NCERT diagram. For understanding purpose, I will draw one more diagram. Imagine a point charge Q, and these are the field lines due to point charge Q. For a point charge, field lines are equally distributed in all the direction. It is like a sphere. Imagine a sphere around point charge Q. In 2 dimension, we use plane angle theta, but electric field is 3-dimensional. Here we consider solid angle omega, 3-dimensional angle omega. This is angle omega. For given solid angle, number of field lines are constant, whatever may be the distance. Here solid angle omega is given by S by R square. Solid angle omega is given by S by R square, where S is area of the spherical surface, area of the considered spherical surface. It is like patch on our imaginary sphere. And R is distance between point charge Q and spherical surface. It is like radius of our imaginary sphere. As distance increases, radius of our imaginary sphere increases and surface area of the sphere increases as R square, because surface area of the sphere is given by 4 pi R square. Hence, area of this spherical surface increases as R square. But number of field lines crossing this area will be same, that is constant. Whatever may be the distance, as area increases as R square, number of field lines crossing this area is constant, but field lines are spreading apart. This shows density of field lines is decreasing. Hence, it represents inverse square law dependence of electric field. Till now, we have studied properties of electric field line due to single individual point charge. Now we move on to one important configuration in electrostatics, that is dipole. Electric dipole is configuration of two equal and opposite charges separated by small distance. Say plus Q and minus Q separated by small distance. Then what are the properties of electric field line for a dipole? We will see that. First point, electric field lines start from positive charge and end at negative charge. You know, for point charge, positive point charge, field line start from point charge and goes to infinity. If you consider negative charge, field lines are coming from infinity and ends at negative charge. But in case of dipole, field lines start from positive charge and ends at negative charge. And next property, in charge-free regions, field lines are continuous and smooth. In this region or in this region, in charge-free region, field lines are continuous and smooth line. That means there is no break in between or there is no zigzag line. It is a smooth line. And two electric field lines never intersect. You cannot draw intersecting lines like this, because at a point electric field have only one direction. So we cannot draw intersecting lines. Electrostatic field lines never form closed loops. Electrostatic field lines never form closed loop like this. In case of dipole, field lines starts from positive charge and ends at negative charge. If you consider point charge, it starts from positive charge and goes to infinity in case of positive point charge. Here you cannot draw closed loop because electric field is conservative in nature. What is the meaning of this? Here, field lines shows the direction in which unit positive test charge moves. If you place test charge at point A, then bring test charge to point B. Here, work done on the test charge is depending on initial and final positions, not on the path taken by the test charge. For example, if you bring test charge back to point A, then work done on the test charge after completing one round trip is 0 because it is depending on only initial and final positions. If work done is 0 after completing one round trip, it shows conservative nature. Hence, electrostatic field is conservative in nature. It do not form closed loop. You may ask, what is the relation between formation of closed loop and conservative nature? Think, if it forms closed loop, test charge will also move in that direction. After completing round trip, test charge would get continuous forward push. Then work done will be greater than 0. If work done is greater than 0, that shows non-conservative nature, which is contradictory. So, electrostatic field is conservative in nature, hence it do not form closed loop. Next property, direction of field line shows direction of force on positive test charges. In which direction unit positive test charge experiences force, that is the direction shown by electric field line. These are the properties of electric field lines due to dipole. We have already completed up to electric field lines. Next topic in this chapter is electric flux. Before understanding electric flux, we think about flow of liquid or flow of water. Imagine water is flowing with velocity v. Let me draw the diagram. Imagine water is flowing with velocity v. Now consider a plane surface which is perpendicular to flow of water. Consider a plane surface of area ds perpendicular to the flow of water. When surface is perpendicular to flow of water, maximum water flows through the surface. Now, rate of flow of water through given surface is depending on velocity of water and area of the surface ds. Now, if we change the orientation of surface, rate of flow of water through given surface will change. Let me draw one more diagram. Imagine water is flowing with velocity v. Now, surface is tilted so that surface normal makes some angle theta with the direction of flow of water. When orientation of surface changes, rate of flow of water is depending on orientation. That is, now rate of flow of water is depending on velocity of water and area of the given surface, and also orientation of surface, that is represented by cos theta here. Here theta is angle between surface normal and direction of flow of water. We define this quantity as liquid flux. In the similar way, we define a quantity in electric field called electric flux. But the difference is, in flow of water, actual water flows through given surface. But in case of electric flux, nothing physically flows. It just measures how much electric field crossing the given surface. I hope now it is easy to understand about electric flux. We already know electric field lines represents strength of electric field. These are the field lines which represents strength of electric field E. Now consider a plane surface perpendicular to the direction of electric field. Consider a plane surface of area delta S, which is perpendicular to the direction of electric field. Now, electric field crossing the surface is depending on magnitude of electric field or strength of electric field and area of the given surface delta S. Here delta S represents it is small area element because electric field may vary from point to point. If it is uniform electric field throughout the area, you can directly take total area S. But here delta S is taken, it represents it is small area element. Next, if we tilt the surface, consider these are the electric field lines which represents magnitude of electric field E. Now consider a surface. Now surface is tilted, so that surface normal makes some angle theta with the direction of electric field. This is angle theta. Now electric field crossing the surface is depending on orientation of surface. It is depending on strength of electric field E and area of the surface delta S and orientation of surface, that is represented by cos theta here. Here theta is angle between surface normal and direction of electric field. We define this quantity as electric flux. And electric flux is represented by Greek letter phi. Electric flux through given surface is given by E into delta S into cos theta. What happens if surface is parallel to the direction of electric field? Think about it. When surface is parallel to direction of electric field, theta becomes 90 degree, cos 90 is 0. Hence, electric flux through given surface will be 0. These are the field lines which represents strength of electric field E. Suppose surface is parallel to the direction of electric field. Surface normal makes 90 degree with the direction of electric field. Here cos 90 is 0. Delta phi, that is electric flux through given surface, becomes 0. Hence, when surface is perpendicular to field, electric flux will be maximum. When orientation is changed, electric flux becomes delta S into cos E into delta S into cos theta. When surface is parallel to electric field, electric flux through given surface is 0. This is the summary of what I have explained. So what is electric flux? It is just a measure of electric field. How much electric field is crossing the surface. We have studied area is a scalar quantity. But here it is mentioned area vector. How area can become vector? When we are dealing with wind or flowing water or electric field passing through given surface, just magnitude of area is not enough. We also need orientation of area, that is direction of surface normal. Here in case of electric flux is depending on magnitude of area and also direction of surface normal. Hence we call it as area vector. Then how to represent area vector? Imagine a plane surface of area A. Now, this is the normal to this plane surface and direction of the normal is represented by unit normal vector n cap. Now, area vector A is given by magnitude of area into unit normal vector n cap. This will give you area vector. When it is plane surface, it has two normals. You can choose either normal, you can choose any normal, but you must be consistent throughout the problem. When it is closed surface like cube or sphere, always outward normal is taken. Outward normal is taken as standard. It need not to be a plane surface always. It may be curved surface also. It may be irregular curved surface. Then how to find electric flux? Suppose it is curved surface. Curved surface is divided into small area elements. Different area elements have different normals. Then total electric flux is calculated. Total electric flux through given curved surface is approximately equal to summation of electric flux through small area elements. Summation of E dot delta S. That will give you total electric flux through given curved surface. This is about electric flux. Now, an important topic comes, that is dipole. Electric dipole. In nature, the existence of isolated single charge is very rare. There exists combination of two charges. For example, polar molecules like HCl, water molecules. There will be two equal and opposite charges separated by small distance. We call this arrangement as dipole. We call it as electric dipole. Let me draw a dipole. Dipole consisting of equal and opposite charges, say plus q and minus q, separated by very small distance d. D is very small in terms of nanometer, or it will be in terms of angstrom. And the strength of the dipole is depending on magnitude of charge and separation between two charges. As distance between two charges varies, strength of the dipole will vary. Hence, to describe strength of the dipole, we introduce separate physical quantity called electric dipole moment. Electric dipole moment represented by small p and is given by q into d, where q is magnitude of charge, magnitude of either charge, because there will be equal and opposite charges. Hence, magnitude of charges is equal. Q is magnitude of charge and D is separation between two charges or displacement between two charges. Displacement between two charges. Here, dipole moment is a vector quantity. It has magnitude and also direction. Dipole moment is a vector quantity and direction of dipole moment follows the direction of displacement. By convention, direction of displacement is taken from negative charge to positive charge. Hence, direction of dipole moment is also from negative charge to positive charge, that is from minus Q to Q. This is the direction of dipole moment P. Direction of dipole moment P is from negative charge to positive charge. Here from minus Q to plus Q. What is the net charge of the dipole? Since dipole consists of equal and opposite charges, net charge of the dipole is 0. Then what about electric field due to dipole? We think when net charge is 0, electric field also must be 0, right? But it is not like that. Even though net charge of the dipole is 0, it produces electric field. Let us see how. Let me consider a dipole again. Dipole consisting of charges plus Q and minus Q separated by very small distance 2a. For convenience, we are taking separation between two charges as 2a so that we can take distance between charge and center of the dipole as a. It will be easy for us. What is the direction of dipole moment? The direction of dipole moment is from negative charge to positive charge. Now we are finding electric field due to this dipole at two different points. One is point on the axis of the dipole and another point on the equatorial line of the dipole. First, let us find electric field at point P on the axis of the dipole. Now point P is on the axis of the dipole. Let R be the distance between point P and center of the dipole. Now distance between point P and charge Q is R minus A and distance between point P and charge minus Q is R plus A. First, let us find electric field at point P due to charge Q. EQ. What is the expression for electric field? E is given by K Q by R square, where K is constant, which is equal to 1 by 4 pi epsilon naught, and Q is magnitude of charge, and R square, R is distance between point and the charge. Here distance between point P and charge Q is R minus A. Hence we get EQ as KQ by R minus A whole square. This is magnitude of electric field at point P due to charge Q. What is the direction of electric field? For positive charge, direction of electric field is outward. Hence, it is away from the charge. It is away from the charge Q. It is along the direction of dipole moment. Away from the charge Q. Hence, the direction of EQ is along the direction of dipole moment. Along P. Repeat the same for charge minus Q. Electric field at point P due to charge minus Q. That is E minus Q equal to the magnitude of E minus Q is KQ by distance between point P and charge minus Q is R plus A. KQ by R plus A whole square. This is magnitude. What about the direction? For negative charge, direction of electric field is inward. Hence, it is towards negative charge. The direction of electric field is towards minus Q. That is E minus Q. Direction of E minus Q is opposite to the direction of dipole moment. Opposite to the direction of dipole moment. Now find the resultant electric field at point P. Therefore, resultant electric field E is given by, since point P is on the straight line, since point P is on the axis of two charges, you can simply add or subtract to get resultant. Here EQ and E minus Q are in opposite direction, hence we should subtract. Resultant electric field E is given by EQ minus E minus Q. Substitute EQ and E minus Q, you will get the resultant. EQ KQ by R minus A whole square, E minus Q equal to KQ by R plus A whole square. You can take K and Q outside because it is common. And take the LCM, you will get R square plus A square plus 2RA minus R square minus A square plus 2RA divided by, in denominator you will get R square minus A square whole square. In numerator, R square cancels, A square cancels, remaining is 4RA. Therefore, resultant electric field E is given by KQ into 4RA by R square minus A square whole square. We already know about electric dipole moment P. Electric dipole moment is given by magnitude of charge into separation between charges, two charges. Because of less space, I am making compartments here. We know that dipole moment P is equal to 2QA. Q is magnitude of charge and 2A is distance between two charges. Now replace 2QA by dipole moment P in this expression. You will get, therefore, E equal to 2PR to KPR by R square minus A square whole square. When you replace 2QA by dipole moment P, you will get E as 2KPR by R square minus A square whole square. Here, separation between two charges is very small compared to distance r. Therefore, when r is far greater than a, r square will be much more greater than a square. Hence, you can neglect a square in the denominator. Therefore, I will write it here. When r is far greater than a, r square will be much more greater than a square. Hence, we can neglect a square in the denominator. Therefore, electric field E, resultant electric field is given by 2 kp by r cube. If you neglect a square, you will get r raised to 4, r by r raised to 4, that is you will get r cube in the denominator. This is the magnitude of resultant electric field at point P. What about the direction? If you observe EQ and E minus Q, R plus A will be greater than R minus A. Hence, denominator is lesser for EQ. When denominator is lesser, the magnitude of EQ will be greater than magnitude of E minus Q. The resultant electric field follows the direction of electric field with greater magnitude. Here, EQ is having greater magnitude compared to E minus Q. Hence, resultant electric field follows the direction of EQ, that is along the direction of dipole moment. The direction is along the direction of dipole moment. Finally, we can write electric field in terms of vector form. That is vector E. Therefore, vector E is given by 2k vector P by r cube. Here there is no negative sign. It indicates the direction of electric field is along the direction of dipole moment. This is the final expression for resultant electric field for point P at point P on the axis of the dipole. Similarly, we can find electric field at point P on the equatorial plane of the dipole. Again, we are considering a dipole consisting of charges plus Q and minus Q separated by very small distance to A. What is the direction of dipole moment? The direction of dipole moment is from negative charge to positive charge. And this is the center of the dipole. Now point P is on the equatorial plane of the dipole. This is point P is on the equatorial line. It is better to say equatorial plane because the point P is not restricted to only one line. If you imagine a plane, this is dipole axis. The point P is not restricted to only one line. The point may be anywhere on the plane. So it is better to say equatorial plane rather than telling equatorial line. So point P is on the equatorial plane. Let R be the distance between point P and center of the dipole. And distance between point P and charge Q is, according to Pythagoras theorem, you will get a square plus r square. Similarly, distance between point P and charge minus q is also root of a square plus r square. Okay. Find electric field at point P due to charge q. Electric field at point P due to charge q is, what is expression for electric field? Kq by r square, where r is distance between point and the charge, that is root of a square plus r square. K is constant 1 by 4 pi epsilon naught. Kq by root of a square plus r square whole square. You will get a square plus r square. What is the direction of electric field? For positive charge, direction of electric field is outward, that is away from the charge. Hence, you will get direction of EQ like this, that is upward direction. Similarly, electric field at point P due to charge minus Q. Observe, distance between point P and charge Q and distance between point P and charge minus Q are same. Since distance is same, you will get equal magnitude for EQ and E minus Q. E minus Q is given by KQ by A square plus R square. EQ and E minus Q are equal in magnitude because distance is same. But what about the direction? For negative charge, the direction is inward. So, the direction of electric field is downward. That is towards negative charge. The direction is downward. Now, we should find resultant electric field. Since point P is outside the straight line, it is outside the axis, hence resultant includes angle. To get resultant, we should resolve these two vectors. Resolve vector EQ. When you resolve vector EQ, you will get horizontal component EQ cos theta and vertical component EQ sin theta. Similarly, resolve vector E minus Q, you will get horizontal component as EQ, E minus Q cos theta and vertical component E minus Q sin theta. Here EQ and E minus Q, the magnitude of EQ and E minus Q are equal, but they are opposite in direction, hence vertical components cancel each other. Only horizontal component add up. Therefore, resultant electric field is given by only horizontal components add up, that is 2 EQ cos theta. What is cos theta here? Since this line is perpendicular bisector of the axis of the dipole, it forms isosceles triangle. Suppose this angle is theta. This angle also will be equal to theta. And extend this horizontal line, you will get alternate angle, that is theta. This one is also alternate angle theta and vertically opposite angle theta. You can consider any right angle triangle. You will get cos theta equal to, cos theta is given by adjacent by hypotenuse. Here adjacent side, if you consider theta, adjacent side is A and hypotenuse is root of a square plus r square. Adjacent side A by root of a square plus r square. Substitute cos theta, you will get E equal to 2 magnitude of E cube, that is k cube by a square plus r square, into cos theta is a by root of a square plus r square. A square plus r square raised to 1 by 2. Therefore, E equal to 2kq by a square plus r square raised to 3 by 2. Therefore, we already know about electric dipole moment P equal to 2qa, where q is magnitude of charge and 2a is separation between two charges. We know that dipole moment P equal to 2qa. Replace 2qa by dipole moment P. Here 2qa. Therefore, electric field E equal to, if you replace 2qa by dipole moment P, you will get k into P by a square plus r square raised to 3 by 2. Now, distance between two charges, separation between two charges is very small compared to distance r. When r is far greater than a, r square will be much more greater than a square. Hence, we can neglect a square in the denominator. Therefore, when r is far greater than a, you will get electric field equal to Kp by, if you neglect a square, you will get r square raised to 3 by 2. 2 cancels, you will get r cube in the denominator. This is magnitude of electric field at point P on the equatorial plane of the dipole. What about the direction? The direction of resultant electric field is opposite to the direction of dipole moment. Opposite to the direction of dipole moment. We can write electric field in terms of vector form. Vector E equal to k into vector P by r cube. Since the direction of resultant electric field is opposite to the direction of dipole moment, you will get negative sign here. Negative sign indicates direction of electric field is opposite to the direction of dipole moment. This is about electric field due to dipole. Even though net charge of the dipole is 0, it produces electric field. This is the summary of what I have explained already. Electric field due to dipole at a point P on the axis of the dipole is given by 2 kp by r cube, where k is 1 by 4 pi epsilon naught. Similarly, electric field for a point on the equatorial plane is given by kp by r cube. You can observe the relation between E axial and E equatorial. E axial is 2 times E equatorial. And also, electric field due to point charge is proportional to 1 by r square. But electric field due to dipole is proportional to 1 by r cube. Here we can observe electric field due to dipole falls off more rapidly than electric field due to point charge.